वेलकम वेलकम वेलकम। तो आज हम जानेंगे बियर लैम्बर्ट लॉ के बारे में। तो हम जानते हैं कि किसी भी स्पेक्ट्रोस्कोपिक टेक्निक कोई भी हो, उसका सभी स्पेक्ट्रोस्कोपिक टेक्निक का जो प्रिंसिपल होता है आपका बियर लैम्बर्ट लॉ ही होता है। बियर लैम्बर्ट लॉ को अगर मैं सिंपल टर्म्स में लिखना चाहूँ तो A इक्वल टू ABC, सिंपल। सो A इज व्हाट? absorbance by analyte in the solution. A is the absorptivity और B आपका जो है पाथ लेंथ होता है। पाथ लेंथ मीन्स डिस्टेंस ट्रेवल्ड बाय द लाइट इनसाइड द सैंपल, दैट इज पाथ लेंथ, एंड सी द कंसंट्रेशन ऑफ सॉल्यूशन। तो कहने का मतलब क्या है, जो अब्जॉर्बेंस है वो डायरेक्टली प्रोपोर्शनल होती है पाथ लेंथ of the light that is traveled by the light inside the sample, that is path length. So absorbance is directly proportional to the path length. This is given by Lambert law. This is Lambert law, and directly proportional to the concentration of the analyte in the solution. This is Beer law. So if you combine them, A is directly proportional to BC, so A equal to ABC, and if you're expressing in molar terms, that A equal to will can molar absorptivity, that is this is molar absorptivity. If the concentration is expressed in molarity, then your epsilon will be molar absorptivity. So this is the Beer Lambert law, that absorbance by analyte in a sample is directly proportional to the path length of the light, is directly proportional to the concentration of the analyte in the solution, and you combine them, absorbance is equal to ABC, absorbance is equal to epsilon not BC. Okay, now if you want to derive that, somebody has to derive Beer Lambert law. So how will you derive? So we know that whenever a monochromatic light passes through an infinite thin layer of samples, say of thickness dx, say thickness is dx, it experiences decrease in power, that is dp. So fractional decrease in power, that is dp by p, is because it is negative, so there is decrease in power, so we will mention negative, that the fractional decrease in its power is directly proportional to the path length, that is dx. So we have taken directly proportional to the concentration of the analyte in the solution. So if you combine them, that is minus dp by p is directly proportional to the dx into c, and minus dp by p is equal to, so a proportionality constant a c dx. Okay, so now I have to integrate on both sides. So if we integrate on both sides, so here if I am integrating from p naught to p, and here I am integrating to 0 to b, so integrating both sides, we will have, this is ln p, here it will be negative, and this is p to p naught is equal to a c, that is x, and here it will be p0. So that way we are integrating it. So ln p minus ln p naught to the negative is equal to acb. So here it will be b only. So if you write ln p by p naught, that is minus, is equal to abc, that is okay to write. And if you remove the logarithmic side, though here will be 2.303, that is log p naught by p is equal to abc. And this is a constant, so this can be incorporated in this constant itself. So it will be log of p naught by p is equal to abc. And then if you apply this, if you want to write it as log of p by p naught, then you can put here minus is equal to abc, and this minus log p by p naught is nothing but the absorbance, that we know. So I will prove it now also, that is minus log of p by p naught is nothing but the absorbance. So here will be a equal to abc. So this way we have proved that I have derived the Beer Lambert law. So here if as concentration in molarity, we can write it as epsilon naught bc. Okay, so this is the way we have proved the Beer Lambert law. And to explain that, some of the terms like absorbance and transmittance, let me explain you. So say if this is a cuvette in which you have kept the sample, and I naught is the intensity of light, or p naught is the intensity power of the light that is incident on the sample, and say I is the intensity of the light that is exiting from the sample. Similarly, p is the power of the light that is exiting from the sample. So if you want to write absorbance formula, that is given by I by I naught, or p by p naught also you can write. So in some books it is written p by p naught, and others it is written I by I naught. Okay, then this is the not absorbance, this is transmittance. So if you want to write the transmittance, that is transmittance is that light which is not interacted with the analyte in the sample. So that light which is not interacted with the sample, that is the transmittance. So transmittance gives the intensity, or the light which is not interacted with the analyte in the sample. So here I the intensity of the light that is exiting from the sample, I naught the intensity of the light that is entering the sample. So the transmittance is given by I by I naught, that is equal to p by p naught. And if you want to write in absorbance terms, that we know that A is equal to minus log of transmittance. So this is the equation of absorbance. So if you want to define absorbance is equal to negative of the logarithm of transmittance. So minus logarithm of I by I naught, you can write it like this. Okay, now if you want to write percentage transmittance, you know that a percentage transmittance will be simply you have to multiply by 100. So this is percentage transmittance. Okay, the percentage transmittance is equal to I by naught, I naught into 100. Okay, now this we have, now we can write it as log of I by I naught into 100. If I do and divide by 100, we do, so I can do it like this, and we know that I naught is nothing but the percentage transmittance. So minus percentage transmittance, log percentage transmittance upon 100. So this will come 2 minus log of percentage transmittance. So we have proved that absorbance is equal to 2 minus log of percentage transmittance. So this way we have explained that absorbance is equal to 2 minus percentage log of percentage transmittance. So absorbance can be written this. So this is the relation between absorbance and percentage transmittance. So we will do some numericals on this in some other video, because this is very important for competitive exam, that how to calculate absorbance for percentage transmittance, or transmittance from absorbance, that can be calculated using this formula, that is A equal to 2 minus log of percentage transmittance. Okay, now I've told you that what is Beer Lambert Law. Beer Lambert Law, as per Beer Lambert Law, say that, so if you want to drive the graph between absorbance and concentration, so here you take absorbance, here you take concentration, the graph yours should be kept linear. So this is the calibration curve, that is linear, that as the concentration is increasing, your absorbance must also will increase. Okay, this is the Beer Lambert Law. A equal to ABC, if path length is constant, say you are keeping it as 1 centimeter, then with an increase in the concentration of the sample, your absorbance will also increase. This is known the Beer Lambert Law. But there are limitations. Some limitations are there for the Beer Lambert Law, that we will discuss limitations. So there are 3 types of limitation. One is fundamental limitation. Fundamental limitation means that are concerning to the law itself. Fundamental limitations are, first is that it is valid for only very dilute solution up to 10 millimolar. Okay, so your Beer Lambert Law is valid for only very dilute solution up to 10 millimolar. Why? Because at higher concentration, what happens is that there occur interaction of analyte, interaction between among the analytes in the sample, and that way they affect the charge distribution of each other, and hence the value of epsilon naught will change. That is, the value of molar absorptivity will change. And since the value of molar absorptivity will change, your the linearity of the Beer Lambert Law will get disturbed. Okay? So this is the first fundamental limitation. Second limitation is that at higher concentration, what happens that diffractive index of the medium also changes. Diffractive index. So at higher concentration, what will happen, that diffractive index of the medium will also change, and this in turn will affect the epsilon value of the analyte, and then your Beer Lambert Law again is get disturbed. The linearity of the Beer Lambert Law is again get disturbed. So this is the first limitation, that is the fundamental limitation we call it. And second is limitation is the chemical limitation. So chemical limitation is what, that if the analyte is undergoing association and dissociation, that is the identity of the analyte is getting lost, so you will have the change in the value of epsilon naught, again the linearity of the Beer Lambert Law get disturbed. Okay, so if your analyte is involved in association dissociation reaction, or there is ionization of the weak acid in a non-buffered solution, ionization of a weak acid in a non-buffered solution, then also the linearity of the value of epsilon naught will change, because you know the analyte and ion will have different molar absorptivity. So the linearity of the Beer Lambert Law is again that get disturbed, and your Beer Lambert Law will get deviated. Okay, this is the chemical limitation. So the chemical limitation is this, and third is instrumental limitation. Instrumental limitations. So two instrumental limitations are, first, that is valid for only monochromatic light. So monochromatic light, you know, that is having is a light which is having vibration in only one direction, and polychromatic light is a light which is having vibration in all direction. So your Beer Lambert Law is valid for only monochromatic light. Why? Because polychromatic light will have different types of wavelength, that a different type of wavelength it is having, and then the molar absorptivity again will change for the analyte at different wavelengths, so that your Beer Lambert Law will get affected. And the second deviation is that if any stray light, that is stray, what is stray light? Stray light is any unwanted light which is reaching the detector. Say if sometimes what happens is that better wavelength selector, if there is defect in the wavelength selector which we are using, then some stray light can also come to the detector, and which in turn will affect your that is in turn will affect the lenient of the Beer Lambert Law. So these are the 3 limitation of Beer Lambert Law. तो इस वीडियो में हमने क्या क्या जाना है, हम जानते हैं, हमने पता लगाया कि एक तो प्रिंसिपल क्या होता है हर एक स्पेक्ट्रोस्कोपी का, Beer Lambert Law क्या होता है, क्या प्रिंसिपल होता है, कैसे हम Beer Lambert Law को डिवाइड करते हैं और उसकी क्या लिमिटेशन होती है। धन्यवाद।